Okay, so we're going to work this final from 2022 to 2023. So 2022, 2023. Okay, okay, so let's begin. The stone is thrown at an initial speed of 11.5 at an angle of 50 degrees above the horizontal from the top of a 30-meter tall building. Okay, so here's my building. Okay, we will assume that it is 30 meters tall. Okay, and then we're going to shoot the rock off like that. This will be 11.5 meters per second. Okay, and the rock is going to go like this, and it's going to hit the ground somewhere over here. Okay, let's see. I'm assuming, okay, we know G. I guess if G is 9.8 meters per second squared, we go ahead and figure out the acceleration in the Y is negative 9.80 meters per second squared. That's going to be hard for me to remember. Acceleration in the X is 0. It looks like, if you've been following along with the way that I do things this year, I organized the data slightly differently than last year. No problem there. All right, so before we get to what we're looking for, let's go ahead and get V in the X and V in the Y. Okay, so here's my X direction, here's my Y direction. Looks like I didn't include that 50 degrees, although I should have, right? So this right here will be 11.5 cosine of 50. This will be 11.5 sine of 50. We know because this side right here is the opposite, so it is the sine, and this side right here is the adjacent, so it gets the cosine. All right, cool. So let's go ahead and plug those into our calculator, and the V naught and the X. We get 7.3921 meters per second. And in the Y direction, we get a positive 8.8095 meters per second. All right, so what else do we know? Well, delta X, that's going to be the distance from where this thing is shot to where it's landing. That's delta X right there. And I don't know what that is. The delta Y, well, we know we're starting at a position on the top of the building, and we're ending at a position on the bottom of the building. I mean, maybe way over to the right, but it's still on the bottom. So it's negative 30 meters in the Y direction. And then what else do we know? I don't think we know anything else. We do know that the V in the X is 7.3921 meters per second because we know that the V in the X never changes, okay? So that's going to, that V in the X and the V in the Y, because those are our finals, those are taking place right here. So here's our V in the X, and then there's a V in the Y right here, right? And they add up to give us our total final velocity. If this is what this thing is going to ask for, I don't know what it. Okay, what's the magnitude of the vertical velocity component as the rock hits the ground? So we are looking for. Let me put some red question marks on the things that we're looking for. So we are looking for this guy. What is the magnitude of the horizontal velocity component of the rock as it hits the ground? So we're looking for this guy right here. It looks like I already, I just kind of filled that in because the acceleration in the X is 0, right? Okay, cool. What is the speed of the rock as it hits the ground? So we're looking for this guy right here. It's not even in our chart, right? So we're looking for V equals question mark. Okay. What is the magnitude of the horizontal displacement of the rock when it hits the ground? So we want to know what is delta X. Okay, and we don't know time. Did it ask for time? It does not ask for time, so that's a nice thing. Okay, so the first thing we're going to do here, we're just going to go little by little. So magnitude of the vertical velocity component of the rock as it hits the ground. So I am looking for V sub Y, this is the final velocity in the Y direction. And it says the magnitude, so this, whatever number we get, we're going to make it positive, regardless of what it is. So because we don't have time, my inclination is to do Vy squared equals V naught Y squared plus 2A delta Y. And I might have done this differently on the key, I don't remember. Anyway, so the Vy's we're looking for, so the Vy is going to be equal to the square root of all that stuff on the right. V naught Y squared plus 2A delta Y. Okay, be very careful with this delta Y. We want to make sure that we put a negative number in there, or else we're gonna mess this up. So positive or negative, square root of V naught and the Y, which is 8.8095 meters per second, Square that, plus 2 times negative 9.80 meters per second squared, times the delta y, which is negative 30 meters. Be very careful about that negative sign there. And, oh, that's not what I wanted. Let's erase that. Okay, v sub y equals, well, I don't know, positive or negative 25.811 meters per second. So the number we'll use if we need it for another calculation is we use 25.811. But in this case, because we only want the magnitude, because that's what it asked for, it said what's the magnitude, we'll say Vy equals, what do we want, 3 sig figs in this problem? Yeah, I think if we look at the original question, oh, G only has 2, so I guess we only need 2 sig figs. So this would be 26 meters per second. Okay, that'll be the reported answer. That's the magnitude of the vertical velocity. Okay. What is the magnitude of the horizontal velocity component? Well, we don't even really have to do any work there, right? Because v naught in the x and v naught in the x are the same because the acceleration is 0. So we can just write this down as 7.3921 meters per second. So that's v in the x. That's the final. And because we only want 2 sig figs, we'll say v in the x equals 7.4 meters per second. Okay, cool. Moving on. Okay, what is the speed of the rock when it hits the ground? So if we want the speed, we're basically going to make a triangle out of these two. Okay, and I think I must have been being kind of nice here, because what I did not do is I did not ask for the direction as well. So the x direction, remember we're going to use the full as many sig figs as possible. So there's my x direction. Oh, sorry, nope, that's not my x direction. Okay, so my x direction is 7.3921 meters per second. And my y direction is negative 25.811 meters per second. So the speed is that hypotenuse, right? And we're not going to worry about the angle, but if we wanted the angle, it would be right there. But we're not going to worry about that, okay? We would do the inverse tangent of 25.811 over 7.3921. All right, so anyway, so that the hypotenuse there, which is just going to be v, it's going to be the square root of vx squared plus vy squared. Okay, so v equals 7.3921 meters per second squared plus the vy, which is 25.811 meters per second squared. We'll square root that. So the magnitude of that is 26.849 meters per second. And if we want 2 sig figs, that will be 27 meters per second. Okay. Yeah, it looks like, if I look at the key, it looks like I didn't do the sig figs quite the right way. All right, so what is the magnitude of the horizontal displacement of the rock when it hits the ground? Okay, so whenever we want a horizontal displacement, you know, the temptation right off the bat is to do this. We want to go delta x equals v naught t plus 1/2 at squared. And in the x direction, this is a nice equation because that little bit right there just goes away. The problem with that is that we don't know time. Okay, so there's a few different ways that we can get time. Okay, so let's go up here. So this is going to be a nice clean way to solve this, but we have to get time first. So if I go up here, usually with these problems, usually we get the time from the y direction. And you know, I've already got, so it's not written into this thing up here, but I've got Vy, I've got the 2 velocities, and I've got an acceleration. So that's going to be the easiest way to get the time. Okay, and that's the way that I'm going to do it, is basically using these 3 things and the v equals v naught plus at equation. Okay, so that's the way I'm going to do it. I will leave some space, maybe on the left, just to show you another way. So v in the y equals v naught in the y plus at. Okay, that a will be in the y. So we'll rearrange that, and I'll say t equals vy minus v naught in the y divided by ay. Okay, be very careful with the signs on this. So t equals, let's see, vy. Vy is right here. Okay, and remember it has a negative sign, so negative 25.811. Negative 25.811 meters per second. Now I'm going to subtract that initial Vy. initial Vy. Oh, right here, 8.8095. 8.8095 meters per second. Divide that by AY, which is negative 9.81 meters per second squared. Okay, so you see all those negatives are going to cancel out all nice for us. So we get about negative what? Negative 34, so it's going to be about 3.5 seconds. And let's see if we do the math, we get about 3.5, dang gummit, 3.5291 seconds. Okay, so then we'll go ahead and, once we have that, we don't worry about the sig figs on this one because we're going to plug it in right here. So delta y equals V naught in the x direction. Excuse me, there's a little x right there that I forgot to put. So V naught in the x, if we go up, that's this number right here, 7.3921. 7.3921 meters per second. And we'll do 3.5291 seconds. So delta x, if we multiply those, 3.5 times 7.5, we're looking in the mid-20s, 26.087 meters. Okay, so we only want 2 sig figs, so we'll call that 26 meters. Okay, and that's how we would solve it. I will note, because I wanted to mention it a second ago, there were 2 ways to get time. This is the easier way. The harder way would be to have used this equation, delta y equals V naught yt plus 1/2 at squared. The difficulty of this equation, so I'll just go ahead and plug in the numbers in so you can see it. Negative 30.0 meters equals V naught in the y. What was that? 8.8095. 8.8095 meters per second times t plus 1/2 times negative 9.81 meters per second squared, t squared. Okay, so as you can see, the problem here is that this creates a quadratic. So we need a quadratic equation. So the way you would do that is you would bring everything over to one side of the equation. So in this case, this should be 9.80, right? So 1/2 of negative 9.80 would be 4.90, and that's negative, but we'll bring it over to the other side of the equation. So it'll be 4.90 meters per second squared times t squared. This thing is being brought to the other side of the equation. So it will become a negative, or plus a negative 8.8095 meters per second times time, plus a negative 30.0 meters equals 0. And you guys may notice I use more parentheses than you guys do, probably. And the reason for that is this identifies that this is A, that this is B, and this is C. So when you're doing that quadratic, it's gonna be much easier when you're plugging those things in. Okay. If anybody needs help solving quadratic formula, I can show you, but that's the gist of it right there. Okay. So basically, if you solve the quadratic here, you'll get 2 roots. Okay, one of those roots is going to be this guy right here, 3.5291 seconds. Okay, the other root is going to be, if you go back to this original equation, or this original thing, it's going to be if you were to track backwards in time, and you were to get the other time, when, we had a velocity of, a displacement of negative 30, right? So that would have been backwards in time. So you'll get a negative root there as well. Let's see, if I look at the key, we can figure out what that is. It looks like it's negative 1.7331. Negative 1.7331 seconds, okay? But that just requires doing the quadratic formula. Okay, so that's how we solve this particular one. Let's go on to test number 2. This was almost certainly just, another, another section of the class. Okay, you throw a ball with a speed of 25 meters per second at an angle 40 degrees above the horizon directly towards a wall. We know where the wall is. Okay, here we go. So here's a wall, 22 meters away. 22.0 meters away. is where you're going to throw your ball at an initial speed of 25.0 meters per second at an angle of 40 degrees above the horizontal. Okay, so here's our picture. I really like asking people to draw pictures, especially because I think it kind of helps them figure things out, right? So it is an exercise in giving me something to grade, but also, okay, so we don't know if the ball is going to be on the way up or the way down, because if I remember correctly, I'm going to ask the students that particular question. So right here, we got 25 sine, because it's the opposite of 40. Okay, and on the horizontal, we've got 25 cosine of 40 degrees. Okay, so those are our initial velocities. Let's go ahead and fill those in. So 25 cosine of 40 is going to be 19.151 meters per second. And V naught in the y, 25 sine of 40 is going to be 16.070 meters per second. Okay, I'm going to assume probably it's going to ask us for this, the delta y right here. There's no way to know for sure, but it seems highly likely. I'll just go ahead and label it. Let's see, what else do we want to know? Or what else do we know? We know delta x, the distance till it hits the wall, is 22.0 meters. The delta y, we don't know. I don't know if we want that yet, so I won't label it yet. Vx, well, we know that we have acceleration of 0. So this one and this one are always the same, 19.151 meters per second. Vy, we don't know. Ay, we know negative 9.81 meters per second squared. Okay, how long does the ball take to reach the wall? So that's the first one, so that means we need to know this time. How far above the release point does the ball hit the wall? It's going to be delta y. And then what are the horizontal and vertical components of its velocity as it hits the wall? So we want to know this guy, and I already filled that one in for you. All right. And when it hits, has it passed its highest point on its trajectory? So for that, that's another way of asking, is Vy greater than 0 or less than 0, right? Because if Vy is positive, it's still on its way up. And if the Vy is negative, then it's on its way down. Okay, so let's go ahead and solve these. How long does the ball take to reach the wall? The nice thing here is anytime you're given a delta x, that is usually, because we almost always know v in the x. So if you know v in the x and you know delta x, then you can always get time. And once you have time, these problems get a lot easier. Okay, so here's the displacement equation in the x direction. Okay, and once you add that nice pretty little x, okay, this term goes away because a in the x is 0. Okay, so now we can rearrange what's left, and we can say t equals delta x divided by v naught x. Okay, so t is, delta x was 22 meters. I've marked it all up, 22.0 meters. Divided by v naught in the x. All the v's in the x are 19.151 meters per second. Okay, so if I go up here, we could say t equals, well, let's see, 22 divided by 1.15, maybe? Ooh, wow, that's really good. I estimated right on. 1.1488 seconds. T equals, we want 3 sig figs on this guy. Let's see here, 3, 3, 3. I feel like this problem is going to be 3 all the way. Yeah, so the 22 was our 3 sig fig, so we're going to use 1.15 seconds. Beautiful. Okay, how far above the release point does the ball hit the wall? Again, as soon as you have time, okay, for all displacements, you're going to use this equation. Okay, whether that's x or y. And for all velocities, you're going to use this equation. Okay, as soon as you have time. I can't think of an exception to that rule. Okay, all right, how far above the release point did the ball hit the wall? So, like I said, we're going to use the displacement equation. Okay, let's put a little y in there. Let's not forget that. Be very careful to remember this squared right here. Okay, this is This squared is a big forgetful thing. The other thing is to remember that the acceleration in the y is going to be a negative number. Okay, so let's go ahead and plug these numbers in. So delta y equals v naught in the y. What is that? 16.070. Okay, that time. Okay, remember we're going to bypass this number in favor of the full number, 1.1488, 1.1488 seconds, plus 1/2. Don't forget that negative sign here. Okay, and that time is going to be squared, 1488 seconds squared. Okay, well, I'm not going to be able to do that in my head very easily. So we're going to get 11.988 meters. Okay, so 3 sig figs, so delta y is 12.0 meters. Okay. All right, what are the horizontal and vertical components of its velocity as it hits the wall? Remember what I said earlier, if you have time, you're just going to use this equation. Okay, in the x direction, this is a childish equation, so we don't even bother doing it. Because, acceleration in the x is 0. Okay, so that means that the final velocity is the initial velocity. So v of x is the initial velocity. What's the initial velocity? 19.151. 19.151 meters per second, but we want 3 sig figs. So v in the x is 19.2 meters per second. Sweet, super easy. You don't even need to show that work, right? Okay, now in the y direction, v in the y equals v naught in the y plus at. This has got a little y on it. V in the y equals, what was the initial in the y? Oh, I guess I have it right here, don't I? 16.070 meters per second. Plus, don't forget the negative sign here, negative 9.81 meters per second squared, times the time. What was the time? Oh, 1.1488. 1.1488 meters per second. So v in the y is, it's, slowing down. It's still on, it looks like it's still on its way up. 4.8003 meters per second. So you see how that's positive? That means it's still going up. Okay. Oh, I didn't mean to box that. Let's see, can I erase that without? I cannot. Well, what do you do? Okay. Vy equals 4. Pretend that box isn't there. Okay. Vy equals 4.80 meters per second. Okay, good. All right. So let's go down here. When it hits, has it passed its highest point in its trajectory? The easy answer here is that Vy is positive. So it's going up. The ball, what is it? Is this a ball? What is this thing? It's some kind of ball. The ball is not past its highest point. Okay. Cool. All right. Last one of these 3. Hopefully this will not take me, the last test I tried to save more stuff and I couldn't get it to save, which was a lot of time and effort that just did not pay off. I guess that happens sometimes. All right. During a fireworks display, we should switch to red for that. A shell is shot into the air with an initial speed of 70 meters per second and an angle of 75 degrees above. So it's basically shot straight up. I wonder if I made this problem up. Anyway, certainly can't copy it very well. 75 degrees above the horizontal, 70 meters per second. Fuses time to ignite the shell just as it reaches highest point above the ground. So this thing's going to go like this, and then somewhere right up here at its highest point, it's going to explode. Okay, there's our picture, or, whatever. All right, so what do we want to know? Well, I don't know. There's our picture. Okay, so the first thing we need to do, here's our V naught in the X, here's our V naught in the Y. One nice thing about these is I've given you nothing but angles with the horizontal, so it's always sine on the vertical and cosine on the horizontal. but just be careful. That is not always going to be the case. Okay, 70 meters per second, sine of 75. 70 meters per second, cosine of 75. Be very careful here. And because this is a nice one where you can kind of picture what those values should be. Note that the vertical should be a lot bigger than the horizontal here. Okay, and if you plug this into the calculator, that is what will come out. You'll get V naught in the X as 18.117 meters per second. And in the vertical, we will get 67.615 meters per second. Okay, let's see. Let's see, what else do we know? Let's go ahead and fill in what we know. Acceleration in the X is 0, acceleration in the Y is negative 9.81 meters per second squared. Okay, let's see. At the very highest point where it reaches up here, okay, here's our delta X. That's how far it went in the X. Here's our delta Y. Delta Y. I don't really know anything about delta X or delta Y at that point. I do know the velocity in the Y direction is 0 because it is no longer going up nor down. And the velocity in the X is the same everywhere. Okay, cool. So now I need to know the height at which the shell explodes. So I want delta Y. What else do I want? What else do I want? How much time has passed between the launch of the shell and its explosion? Okay, always got to be careful when we see time in these things. We want to make sure that we're not going to end up with a quadratic. Remember this. Okay, here's the equation that will give you a quadratic. Delta Y equals V naught T plus 1/2 AT squared. And it's only going to happen in the Y direction for these types of problems. And you have to have all three of these elements for it to happen. AY, that's why it only happens in the Y direction. We do have an AY, but an initial velocity in the Y direction, which we have, and a delta Y, which if I'm going from this point to this point, this equation is going to give me a quadratic. Okay, so that is something to be concerned about. Okay, so when you see time here, we want to try to avoid using the displacement equation if we can, because that displacement equation is going to give us a quadratic, right? So the way that we would normally do it is, we don't have time yet. So usually what you do, if you don't want to end up there in this equation, let's avoid that equation. So what you're going to do is you're going to solve for Vy first. And since you don't have time, usually the best way to get that is this equation. Okay. Once you have V sub y, then you can get time out of this equation. Vy equals V naught y plus AT. Okay. And I don't remember exactly how this problem is going to work out. But that is a strategy that works out usually. Okay. So anyway, so when we see time down here, how much time has passed, just, be wary. Okay. When you see time, you want to try to avoid this if you can. Okay. If you cannot, then the quadratic formula is negative b plus or minus the square root of b squared minus 4ac divided by 2a. Okay. It's a bear, but it can be done. Okay. So anyway, okay, what is the horizontal displacement of the shell when it explodes? We're going to want delta x. Okay, so delta x is right here. Okay, now delta x is easy. Let me just go ahead and let me kind of map this out. Delta x is easy because we're already going to have time. Okay, so if you have time, this is going to be V naught T. And remember the rest of that equation is 1/2 AT squared. But remember that AT squared goes away. Oh, sorry, that was an AX. Okay, that whole thing goes away because AX is 0. Okay, so the horizontal displacement is not a terribly difficult question as long as you have time. Okay, I will say that if you can't get time, if you're like, if you're working and like whatever, you're running out of time, you can't get time, you're stuck on this particular problem, then what you do is you go down to this one and you say, assume, okay, I usually mark my assumptions with little stars like that. Assume t equals, say, 5 seconds, and then solve this problem. Okay, I will grade it in such a way as if the time were this, I mean, obviously you will miss this one because you didn't finish it, but you can still get whatever points are allotted to this point. Okay, so please use this strategy if you run out of time. Okay, there's no reason to miss everything after that point. Okay, so let's get the height at which the shell explodes. Okay, and the key to that is, right, so it's going to be here, right, because we're looking for a height. So we're looking for delta y. Now, if we had the time, then, and we can actually get the time pretty easily from down here, because this one's actually pretty clean to get the time. But let's assume we don't have the time. Okay, let's assume we haven't done this yet. Now, I recommend if you get stuck, do these out of order. You don't have to do them in order. A lot of times the problem will kind of lead you in a particular direction, but you don't have to do them in order. The easiest way to get the time right off the bat on this one is Vy equals V naught y plus AT. Okay, so if you decided to get the time right off the bat because you're like, that's going to make things a lot easier, you could do this right here. And then once you did that, you could go up here and do delta y equals V naught t plus 1/2 AT squared. Okay, and that will work out just fine for you. If you did this first, then you came back up and did that. However, let's assume that you're hard-headed or it hasn't occurred to you to do them out of order. And if we want a height and we don't know time, okay, if we don't know time, well, if you don't know time, then always you're going to lean into this equation. Vy squared equals V naught y squared plus 2a y delta y. Okay, we're solving for delta y, so I'll rearrange this, and it will be delta y equals Vy minus V naught y squared divided by 2ay. Okay, as always, be very careful with your signs, but especially on one like this. Okay, so delta y equals, well, the final velocity at the top is 0 squared minus the initial velocity, 67.615 meters per second squared, divided by 2. Don't forget that negative sign right there. Okay, if you end up getting a delta y that's negative, most of you guys will just ignore the negative and move on. I would use it as a sign that there might be something wrong. Okay, so just, be aware of that. Okay, so we're going to go up here, and I'll get delta y equals, let's see, 67 squared. What are we looking at? 4,500 divided by, 20? So 250 or something? Let's see, 233.02. Wow, I didn't think I would be that good on this one. Okay, those are some rough numbers. Okay, we want 3 sig figs on this one, I believe. We got 3. We got 3. That's all the numbers were given. Yes, we got 3 sig figs, so we'll say 233 meters. That's my delta y. Remembering, if I need to use a number for a future part of this problem, that's the one that we're going to use. All right, let's see. How much time between the launch of the shell and the explosion? I think in this particular case, this is the easiest way. Okay, so let's go ahead and do that. V equals V naught, so these should have y's, plus AYT. Going to rearrange that to T equals Vy minus V naught y divided by AY. Okay, again, be very careful with the signs here. I can't stress that enough. Okay, so the V and the y, the final velocity is 0 minus the initial velocity, 67.615 meters per second. Okay, divided by AY, which is negative 9.81 meters per second squared. If you somehow get a negative sign there, you've done something wrong. Okay, so let's go back and check your work. Okay, T equals, 68 divided by 10, 6.8-ish. So I'm getting 6.8925 seconds. 25 seconds. I really should have given this class more space. 6.89 seconds, okay? So again, remember, if I need this number for another part of the problem, we're going to use the full number. All right, so what is the horizontal displacement? As always, if you have time, horizontal displacements are just calculated straight up from this displacement equation. So delta x equals what's V naught in the x? Not very fast. 18.117. 18.117 meters per second times that time, which is this number right here, 6.8925 seconds. So delta x, if we multiply those two bad boys, puppies, whatever the nomenclature of the day is, 87 meters. Okay, so the delta x is 125 meters. Okay, so it gets a lot more up. How far up did it go? 233 meters. It went to the right, 125 meters. Interesting. Okay, so more up than to the right, which was to be expected by that angle, right? The steep angle we started with. However, gravity was working against it in the vertical. Okay, so it didn't go a ton higher, but but higher. All right, so if you zoom out, that's the work we've done. Take care of yourself. Okay. Know that this test is important, but there's a lot more important things in this world, namely you and your mental health and your family. So I hope you're having a lovely evening, and I'll talk to you later.